Welcome to our course, Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter B. Galvin, published by Wiley Publishing. In the last lesson, we had our introduction to the topic of process synchronization. We had just mentioned a problem that occurs when two processes are interacting with one another. So why don't we pick up where we left off? Now let's see how concurrent or parallel execution can contribute to issues involving the integrity of data shared by several processes. Let's consider an example of how this can happen. Earlier, the authors described how a bounded buffer can be used to enable processes to share memory. Don't forget that the memory management system is responsible for assigning jobs to memory and ensuring that those jobs do not intrude on one another's memory space. In their earlier example, they offered a solution that allowed at most buffer size -1 items in a buffer at the same time. Their solution in that unit did not address the issue of processes accessing the shared memory concurrently in a manner like our helicopter problem. Suppose we want to modify the algorithm to fix this deficiency. One possibility is to add an integer variable, counter, initialized to 0. Counter is incremented every time we add a new item to the buffer and is decremented every time we remove one item from the buffer. The code of the producer process can be modified as we see here. In this example, the producer is trying to add something to the buffer, as you can see in the remark, produce an item and next produced. Then the producer starts a loop indicated by the line while counter equals buffer size. As you can see, if the counter and the buffer size are the same, in other words, the buffer is full, then nothing happens. Otherwise, the job continues to add to the buffer with the next two lines. So at this point, it's increased the value of buffer size. Then it increments the counter and starts over until the counter equals buffer size, meaning it's full, at which point it must wait until the consumer routine removes something from the buffer. The code for the consumer process can be modified as seen here. Of course, if the counter is 0, then there's nothing to consume, and I'll let you figure out the rest. Although the producer and consumer routines we've just seen are correct separately, they may not function correctly when executed concurrently. As an example, suppose the value of the variable counter is currently 5, and the producer and consumer processes concurrently execute the statements counter increment, which is counter plus plus, and counter decrement, which is counter minus minus. In other words, the producer increments the counter and the consumer decrements the counter. Following the execution of those two statements, the value of the variable counter may be 4, 5, or 6. The only correct result, though, is counter is equal to 5, which is generated correctly if the producer and consumer execute separately. In other words, both the producer and the consumer may be accessing the buffer at the same time, and depending upon which one finishes first, the buffer may or may not be correct. It would be possible for the producer to finish before the consumer and begin another loop, which would increment the counter to 7 before the consumer had a chance to decrement the counter to 5. Then when the consumer does decrement the counter, its value will become 6, which is not correct either. Our next slide will show us the value of the counter may be correct. Note that the statement counter increment may be implemented in machine language as shown here, where register 1 is one of the local CPU registers. Also, the statement counter decrement is implemented as shown here, where again register 2 is one of the local CPU registers. Even though register 1 and register 2 may be on the same physical register, remember that the contents of this register will be saved and restored by the interrupt handler. The concurrent execution of counter increment and counter decrement is equivalent to a sequential execution in which the lower level statements presented previously are interleaved in some arbitrary manner. One such interleaving is shown at the bottom of the slide. Notice that we have arrived at the incorrect state, counter equals 4, indicating that 4 buffers are full, when in fact 5 buffers are full. If we reverse the order of the statements at T4 and T5, we would arrive at the incorrect state, counter equals 6. We would arrive at this incorrect state because we allowed both processes to manipulate the counter concurrently. A situation like this, where several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the order in which that access takes place, is called a race condition. To guard against the race condition that we see here, we need to make sure that only one process at a time can manipulating the variable counter. To make such a guarantee, we must make certain that the processes be synchronized some way. Situations like this are not rare on a computer system, since in operating systems, different parts of the system often manipulate resources. And as we have already discovered, the prominence of multi-core systems has brought an increased emphasis on developing multi-threaded applications. In such applications, several threads may be sharing data while running in parallel on different processing cores. As you can imagine, this is a serious problem. We must ensure that any changes that results from activities do not interfere with each other. Well, this is a good place to stop. We've identified a real problem, haven't we? That two concurrently functioning processes can, in fact, collide and create a situation where the data is not correct. In the next lesson, we will start looking at how to fix that. So take a break, study your notes, look at this one over very carefully, and when you're ready, come on back and we will continue.